Hello folks in 114. Today we're going to be covering section 4.2. Still got the calendar here. Okay. Today is Wednesday. Or am I in the wrong month? Sorry. Wednesday, May 19th. I gotta get rid with the month here. June 19th. So section 4.2 per the schedule. Right. The packet that I have for you looks like this. It's if you've been looking in pages at this point, you'll notice that there are basically groups of the section materials. I try to separate them by color and a little bit of an obvious gap between them. Anyhow, this is the first page. I have to upload this right now because I made this last night. But this is to help organize. This is blank on purpose because I want to fill it in with you to clarify. The activity is what helps you remember it. It's a good technique for teaching. Right? What is really important is, since we're going to be discussing Babylonian and Mayan numeral systems, you want to have the character set from each of those. All right. As you can see, this is quite short for the Babylonian one. It's probably the oldest system, hence it is not too complicated, but to express a quantity is not the easiest thing. There are two models that we would basically use if we wanted to translate from Babylonian or Mayan into Hindu Arabic. So I tried to make this as a reference. And then there are the actual procedures involved, right, in general. All right, I'm going to go through this with you. Starting from, I'm dubbing it alien because it's not something that's familiar to most people, Babylonian. And then converting it to the familiar system, which is Hindu Arabic, right? This will be the same strategy when we get to section 4.3, so tomorrow. Then there's going the other way, starting with what is Hindu Arabic, the familiar system, and then converting it to the alien hieroglyphics. So there's a different procedure. In this case, it would involve dividing. All right. And then there are the examples with the solutions. I just swiped these from the book, screen captured them, and pasted them onto one PDF. Okay, so if you're following along, do try to print that out, and we'll go over this now. I'll turn on my projector. And I'm boiling some coffee, so if I hear a beep, I'm just going to set my stove. Come in and turn on. There you go. I may have to move my camera, as I often do. Alright, scoop this over. That looks crooked. It's like somebody been messing with my camera. It's not me. That's pretty good. Alright, now yesterday I started with an overview, which I want to begin again, of the different topics in chapter 4 where we are. Okay, that's very blurry. Let's see if I can adjust this. Sorry. Somebody's been messing with my camera. That's pretty good. Okay, all right. We yesterday, if you watched that video, began chapter 4. Put this in red. It's probably the most obvious. Systems of numeration by discussing the 3 out of the 4 ancient systems, the additive, the multiplicative, and ciphered. Right, today we're going to be doing the positional systems. Basically, from here to here is section 4.1. Right, and the topic for today, just these two, is section 4.2. Right. these are categorized as positional or place value systems, right? And you'll see why when we get into it. Specifically, we're going to talk about Babylonian, which is probably the oldest system of writing and of numeration, and then Mayan, which is a baby in terms of the age of it, but still quite old. This is from maybe slightly more recently in history. The Hindu-Arabic system, which we use, is past the point of recorded history being 0. Right? So I just thought I should probably more accurately classify this as modern. It is still a positional system, right? And the subsequent topics that we get into, all of this stuff is 4-3, right? So that would be tomorrow's topics. Okay. All right, this is a summary. What did I tell you from last time? The additive systems are basically repeating a symbol. That's the basic idea. To convey the amount. That was from yesterday. That's my beep. Sorry. Your coffee's burled. Okay. The traditional Chinese system is the system we have to illustrate multiplicative. What's interesting about this is that you have the numbers written vertically, stacked, to give it some distinction. There's more to each of these, and I went into it yesterday, but just to review really quickly. Ionic Greek. All right, this is basically when you have letters to represent numbers. Now you might say the Romans is like that, and that is true. But there's quite a lot of these, right? And the Roman system, Roman numerals, is quite finite. There is just 6 symbols that they use, right? In the case of Ionic Greek, there's 27, right? So that is double-ciphered. Now, these two that we're getting into, Babylonian and Mayan, right? To add some distinction here, right? The idea of a positional system in general is that the value of a symbol depends upon position. In a sequence. Okay, so that's where we're at today. And that is section 4.2 in a nutshell. Now, to help clarify, let me switch slides here. And we'll go to this new one that I made yesterday. I'm sorry, I'm just trying to make sure if I have all my stuff together here. Okay. These are positional value system, positional or place value systems. So, there are 2 key features here. Alright, to begin with, a positional or place value system has these 2 characteristics. There is a base number that defines the system. We using the Hindu-Arabic system, use a decimal system, which means that we are base 10. All right? We don't really dwell upon it too much, but that is an alternative perspective of it. Anyhow, there's a base number that is essentially a multiplier, right, and is consistently the same base. And then there's a set of numerals that you're allowed to write with, right? These are the parts in the box that you have to work with and nothing more, right? Now, just to be clear also, this is what it would look like if you wanted to be fancy All right. A base is the bottom of these two generalizations here. The number, say, for example, 10, all right, and then an exponent that would be adjacent to it. So if you happen to, as an example, be base 10, right, which is what we have, the Hindu-Arabic system is base 10, then the only thing that would change is the value of the exponent. So you could have a 0 here, right? You can have a 1 here, a 2 here. It's usually just a positive integer, meaning it's a whole number from 0 to, I'll include 0, 0, 1, 2, 3, and so forth. All right. Beware of a couple of things if you feel a little sketchy about exponents to begin with. This particular portion of it is the exponent. Right? And the exponent is basically a more sophisticated instruction to multiply. More sophisticated than what is usual. Right? This is the base number. This is the number that repeats. Iterated is the way of saying it fancy. The number iterated. The whole thing, the whole kit and caboodle, this part and this part in tandem would be referred to as a power of whatever the base is. So if you had, as I mentioned before, 10, all right, to the, say, first, all right, that would be a power of 10, all right, not a power of 1. There is a common misconception that it's the exponent that is the power, but in reality you would say first power of 10, or in theory, the second power of 10. That's totally legit, but don't say to the power of 2 or to the power of 1, because that is implying the wrong thing is the base. The actual base is what this is a power of. Okay, here's another example of that. This is the third power of 2. Or you could say 2 to the third power. Those are perfectly legit as far as English is concerned. All right. Do not say, not to be grammar Nazi or anything like that, but try not to say 2 to the power of 3, because that is not correct. Right? Because this English phrasing, the way that it's written, power of 3, is implying that 3 is the base, when in reality it's not. Right? So just be mindful of that. Don't say this way. You will hear people on the televised news make that mistake. You will hear your professors make that mistake. You will hear your friends make that mistake. I've seen it in textbooks written wrong. All right. Just don't do that. English is complicated, unfortunately, and that would be why you have to forgive a person. Right? There's the vernacular, ordinary way of speaking. Everybody knows what you mean, but these are the correct ways to say this. Right? Here's another example of English being kind of complicated. We have the number 2, and then we have the word to, right? Going to someplace. Right? 2 to the third power of 2. This is the most precise, perhaps, because it is implying directly what is it a power of. Right? This is a power of 2, this is a power of 10, because that is the base and that is the base, respectively. Right? Now, another thing is that it involves multiplication, but it's a more sophisticated instruction to multiply. Right? What it is telling you is that you take the base number and you iterate it. So if it's a base 2, then it's a 2 here, and a 2 here, and a 2 here, and then you multiply. Right? It is not 2 times 3. Right? 2 times 3 would be 2 plus 2 plus 2, as opposed to 2 times 2 times 2. Right? What's 2 times 3? 6. What's 2 times 2 times 2 times 2? 3 of them. 8. this is correct for 2 to the third, and this is correct for ordinary multiplication. Anyhow, this is not ordinary multiplication, all right? It's an exponent. So don't do this, all right, when you have to use an exponent. Okay? All right, now, another bit of review here. There's a standard form of a number, and then there's an expanded form. We don't want to do it wrong, so let's talk about it. All right. The standard form of a number is more or less the ordinary way that you see it written, as a sequence of digits grouped together. All right. Really should put a comma here, but you're less likely to see that, at least in our textbook. Anyhow, some books they don't say standard form, but I favor that way because I think it helps distinguish. All right. Expanding it would be to take the digits and put them in their own little pockets here. Notice the parentheses. So I'm not too creative, as you can see. I put 1, 2, 3, 4, like the combination of my luggage, right? All right. 1, 2, 3, 4. All right. And yes, the parentheses is unnecessary because I really want to make sure that you know that you have to multiply before you add. Okay, that's the order of operations anyhow, but this would definitely solidify that. The little groupings is basically meant to draw your attention. Right, this is more important. Anyhow, as for what they're each being multiplied by, they are multiplied by the value of their position, right? The places that these things are sitting. Now you probably have some inkling from earlier in your life that this is the ones place, right? And that this is the tens place, and that this is the hundreds place, and this is the thousands place, right? And in theory, a person could write that. They could put 1,000 here, right? They could put 100 here. They could put 10 here, and they could put a 1 here, right? But to get your feet wet, right? To get you acclimated to the Babylonian system that is forthcoming, and as well the Mayan system, right? Instead of writing something in an ordinary number as 1,000, 100, 10, or 1, what I will do is I will write them in the style of their equivalent, a power of 10. 1,000 is the third power of 10. 3 zeros, exponent of 3, in the case of 10 at least. 100 is the second power of 10. 2 zeros is an exponent of 2. All right. 3 is 10 to the first, which is, I know, superfluous, right, to even bother writing that, but this is keeping with that stylistically, right, the aesthetic, right? And then there's 1. Believe it or not, as silly as it may sound, you could write the quantity of 1 as a power of 10. And in that case, it would be 10 to the 0. Okay? So, standard form, the ordinary way you write a number. Expanded form, for our purposes, is to write it like this, as groups of powers of 10, all right, times the number, okay? And you could, if necessary, you could always, separate out these numbers here, here, and here. That would be a little bit more keen and similar to the Babylonian system that's forthcoming, as I mentioned, right? Just realize this, right? We're going to write things not so much in the actual ordinary number, but in powers instead. Okay. All right. Now, as for what the Babylonian system looks like, you definitely want. I swiped this from the textbook to summarize because it's very useful. These are the character sets. These are the elements of the Babylonian system and the Mayan system, and you absolutely would want to have these keys in order to translate. Babylonian, which is derived from Sumerian, right? They are contemporaries in history, really. So something like, the oldest Sumerian civilization was from approximately 5000 BCE, something like that. And the Babylonians were their contemporaries, a little bit further along in time, but they coexisted. Anyhow, Babylonian is derived from Sumerian, and this is the style of writing that they had, wedges, right? They would take a reed, cut off the top of it to make it narrow, and press it into clay, right, to make a list of things. Anyhow, it's not too complicated, as you can see. It just involves two elements, right? If you want to get fancy, you can put it in fancy braces, right? There is a symbol for 1, and there is a symbol for 10, all right? They're not actually referred to as a railroad spike and a boomerang, but if it helps you to remember them, all right, that's what I do myself, to be honest with you, all right? Railroad spike and or a nail, or you could say some kind of a wedge. And this definitely looks like a boomerang. There is one other thing that you might see, and I'm going to bring it up again later, which is a wedge that looks like this in tandem with a wedge like this. So not quite the same symbol here as this. It's facing the other direction, and it's a little. I'm just stylizing it really, but it looks like that. One thing above the other. This is the combination that means subtract. Okay, so if you see something on one side of it, those two things together, and then something on the opposite side of it, just know that it's telling you to subtract these things. Okay, there is a word for a symbol like this, which again you're not responsible for, but it's just kind of a funny word. And if again it helps you remember it, flukerang. That would be this thing up here. All right, that's from Virgil Exeter, from the 1950s. A flukerang. It's a style of an arrow, basically. The Mayan system is cool because I think it's very intuitive. Right now, you notice one thing that's distinct from Babylonian immediately. There's a symbol for 0. All right, and it kind of looks like a 0. To me, it sort of looks like a coin that is, you're looking at it at an angle, so you see the edge of it. All right, I'm not really sure what it's supposed to represent, but it's round certainly, and it does represent 0. The things that I like about the Mayan system are, not to corrupt your opinion, it's very intuitive. All right, the amount of 1 is a single dot. The amount of 2 are 2 dots. The amount of 3 are 3 dots. The amount of 4 are 4 dots. And then when you get to 5, rather than draw 5 dots, all right, you get a solid line. All right, and then everything else is basically derived from that. All right. So if you wanted to basically express the quantity of 6, it's 5 and then 1. If you wanted to express 7, it's 5 and then 2. If you wanted to express 8, it's 5 and then 3, and so forth. And then when you get to another 5 in a row, it's 2 lines. All right, it's very intuitive. At least the first time that I had seen this, I'm like, oh wow, that's very sensical. All right, that's totally cool. 15 is 3 lines. All right, in theory, I suppose 20 would be 4 lines. All right. It's one thing that's about this that's interesting too. When in algebra, you know that when you graph lines, all right, you have to basically draw a line over the dots that you have plotted on the coordinate plane, right? What this illustrates is that a line is really just a bunch of dots infinitely, connected. Eventually, you'll flesh out the picture of a line if you plot enough coordinates. Right. Now this is not graphing in 2 dimensions, but there is some symmetry there. Right? The sort of idea of, all right, once we get to 5, it's practically a line anyway. Right. Anyhow, there's another bit of information here which I included about the original symbols from Myanmar over here, but that you're not really responsible for that. That's just an interesting tidbit. They use the, look over here, it says, for example, although the people of Myanmar use the traditional Hindu Arabic symbol numerals, they also use the following, right, which is kind of cool. Okay. Anyhow, we use the Hindu Arabic system today. Why? Because it really is the most practical, right? And when something becomes universally grasped, like the metric system, all right, then it is even more practical because everybody's using it. All right. So now to summarize the three systems that are positional, I made this diagram to help fill in here. So where is it? There we go. Okay. This is for the sake of comparing and contrasting. In terms of time, I hope this marker cooperates. Yes, that works. Okay. Blue is dying today. Babylonian, right, which again is derived from Sumerian. Its heyday, I would suppose, is something about 2500 BCE. You're not responsible for any sort of dates. This is not a history class, but that's just to kind of position you in relation to it. All right, so here's the timeline. All right, here's today. All right, here's 0. All right, and here's Babylonian. All right, 2500. So you can think of it as negative 2500 if you like. Mayan is a little bit younger, all right? It's more recent in history. All right, so this is about 1000 BCE, before the Common Era is the way that we're tending to write BC nowadays, just to be respectful. All right. Hindu-Arabic, again, the system that we use, all right, is the baby here, all right? 600, wow, that's a nice green, actually rice was. Is CE, right? So, here's Babylonian, Mayan would be something like right here, before 0. Alright, and Hindu-Arabic starts about here, 600. So, plus 600, minus 1000, if you will, and minus 2500. Right. CE is the alternative we're using instead of AD, because that's I went to Catholic school myself, but you know, Anno Domini is in the year of our Lord. Right. Anyhow, that's fine. It conveys the same information. I actually like pluses myself. Anyhow, so this is to position you in time in relation to these things. We have been using, as you can see, the world, all right, the Hindu system, since at least this far back in time, all right, but it took a while to get to the point where it was universally employed, all right. Europeans, not until the Middle Ages, really. And even that's what, if you've ever heard the name Fibonacci, is one of the reasons he's significant in history of math, is because it is he who basically helped popularize the number system that is the Hindu-Arabic system in Europe. Right. Anyhow, where do these things come from? Well, Babylonian is from the Middle East. All right. Mayan is from Central America. And Hindu-Arabic is also technically in the Middle East. Started in India, so the subcontinent. But to generalize a little bit more, the Middle East. Right. What is perhaps more significant is these two systems are from what you might call the Old World. Right. So even if they didn't start in exactly the same places. The people living in India and the people living in what is modern day Iraq, all right, certainly were aware of each other, right? So, and there was trade routes at the time. So, how does information spread? Through trade, really, right? If you were aware of another culture, you might adopt some of that culture, one way or another, right? Central America was completely unknown to these groups of people at this point, and yet they developed a system independent of them. They developed the concept of zero independently. That's fascinating, actually. Right? This is the New World. Now, what is it? Well, let's get some terminology out of the way. There's a fancy way of referring to this. The Babylonian system is what, instead of base 10, which is Hindu Arabic, this is a base 10 system that we use. The Babylonian system is a base 60 system. And you might wonder naturally, why is that? You know, there's reasons I'm going to get to in a moment. In fact, I left the blank spaces underneath these to explain what we think is the reason. Mayan, just before I get to the fancy way of saying any of these, is basically a base 20 system. Right? I'm saying about, you know, because it does employ another number, right? And it also includes 18 in it. So it's not exclusively involving multiplication of some powers of 20. You also, at some point, you'll see in the models, you will have to multiply by 18. There is reason for that as well. Right? There is the fancier way of referring to these things, rather than base 60, base 20, or base 10. I may be mispronouncing this, and I don't want to misinform you, but a base 60 system is called sexagesimal. Sexagesimal. This math is so kinky, right? You know, not as asexual as you can possibly get. Some people may say sexagesimal. I couldn't really tell you what was the proper pronunciation. How to spell it is probably more important. Sexagesimal, all right, is a base 60 system. Something that would be genuinely base 20 is vi or vigesimal. Vigesimal, 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 vigesimal. I'm not sure. All right, English again, complicated. Lovely language, but there's a lot of conflicting sets of rules, even to a native speaker. All right. Thankfully, this one, base 10, is quite easy because it's so familiar. It is a decimal system. When we get into section 4.3, we talk about binary and octal and hexadecimal systems and duodecimal systems, which is base 12. All right, you'll see this sort of nomenclature more. All right, but if you want to be pretty plain spoken, you could just simply say it's base 10, base 20, base 60. All right, it conveys the same meaning. Now, there's more to this. So, if you're curious, and I understand you probably would be, let me move up a wee bit here. And show you some of the fun facts. Trying to stick with distinct colors for these, so blue, red, and green. reluctantly. I probably shouldn't have put green adjacent to red because it's sometimes hard for people who have trouble with those colors. All right? You, as a teacher, you do have to be mindful of that. If you're going to make something that is multicolor, that's good. All right, it will add some distinction and it will reinforce the concept, but try not to keep red and green too close to each other. It's hard to see. Anyhow, where does the idea of having a base 60 system come from? Right? Or even further still, a base 20 system. It's intuitive to us humans, modern humans, all right, where base 10 comes from, right? Is anyone going to tell you it comes from our hands, right? It's intuitive to us because we have 10 fingers. We also have 10 toes, but having to wear shoes has kind of limited us in a way, I wouldn't want to be barefoot naturally, but we understand, right, what the origin of 10 is and why it is so intuitive to us. Because we have 10 fingers and 10 toes, but we only use the hands really when we're counting. Right? So that's a badly drawn hand, sorry. But it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright? Is where the 10 comes from. Alright? The Mayans basically also included their toes, alright, in this idea. Alright? So, less limited in that respect. Given pointy hands in this case. And to illustrate feet, I will draw silly looking toes here. So it's understandable where the number originates from. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now you might wonder, well, where's the 18 factor into this? The reason for 18 is because the number 20 times 18 equals 360. All right, 18 times 2 is 36, and another 0 is 360. They did this to basically make their system match in some way, conform to the calendar. All right, our calendar is 365 days in a quarter. Right, we're a little bit more precise in our timekeeping. All right, nowadays, but even our calendar is not perfect. All right, but the Mayans had a 360-day calendar. All right? So, forcing this number into the 20, the seemingly sacred amount of 20, all right, forcing this number 18 in tandem with this would produce 360. All right, if numbers are sacred, and they are, all right, to the Mayans and to us as well, they really should be. All right, it would seem to make sense. All right, this number 360, which is approximately how long it takes for the Earth to travel around the sun, would seem to be an important number, right? So therefore, your number system should incorporate that. Right? As for the Babylonians, all right, it does come from your hands as well, but this is the theory. Imagine you have one hand for record keeping and the other hand for counting. That should be, if I do this perhaps correctly, like that orientation. A hand, all right, can also be, if you look at it, right, segmented. Right? So, it is thought that the segments that are 3 on each of the 4 fingers, I'm excluding the thumb in this case, are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right? 12 is the sacred number. And if you're trying to keep track, just using your hands of counting, which would be practical, right? You use the other hand, all right, to go, well, this is the first 12, all right? And then to sort of illustrate the person keeping track here, once they extend the finger, all right, that would be the second 12, and then the third, and then the fourth, and then the fifth. So what is 12 times 5 is a maximum? It's 60. Right? 60 was the sacred number, right? As opposed to what we regard the sacred number, 10. Anyhow, the numeral system is limited to the base number and the implement of choice to write with. They didn't have ink, at least not to write with at that point. The Egyptians used ink, all right, but the Babylonians, which is derived from Sumerian, which predates the Egyptians by a little bit, all right, they were using clay, all right, to write things. All right. So that's fascinating, though, isn't it? Where the number originates from, just in your hands, right? The one thing that you should impress upon your own students when you get there, all right, when you put in charge of them, all right, teach them that there is a relationship, right? There are some things that we kind of take for granted, like temperature scale, right? Why is it so hard for an American to sort of adapt to the Celsius scale of temperature? I would argue it's because they grew up with this other system, the Fahrenheit scale, all right? And they have a feeling associated with those numbers. So it's very hard to sort of deviate from a feeling. You know, it's ingrained. You know, it's conditioned. All right? If somebody said to you, oh, it's 20 degrees outside, an American would intuitively go, brr, you know. Why? Because they grew up with the number 20 being 20 Fahrenheit, and that's cold, you know, as opposed to 20 being room temperature on Celsius scale. All right, anyhow. So there's a relationship to numbers, whether we give them credit or not. We should teach our kids that. Right? It's also good to exercise mental flexibility. Right? Now, another interesting feature here for contrast is that the Babylonians, in spite of the sophistication of their math, they didn't have zero. Right? I guess the argument would be, and I'm just riffing here, right? Zero is a symbol, which is a thing. It's an idea. All right. So if zero, without the idea of it being the go-between negatives and positives, is representative of nothingness. All right. Why would you have a picture to represent nothing? You know, it would seem kind of silly. Well, in order to employ more sophisticated math like algebra, you need zero. You know? Again, the Mayans, to their credit, they did not communicate with these two civilizations. All right. Right, they existed between them anyway, but even if they did overlap, they were not aware of each other. And independently, they had zero. And in fact, the symbol for zero looks very much like a zero, right? It's that sort of coin in profile, at least that's my corrupted way of looking at it. Or sort of a ball, all right? A deflated ball, like a football. Our system has a symbol for zero. All right. And we can thank the Hindu-Arabic culture, especially in India, is probably where it most likely started. All right, this number system, base 10. All right, for that, all right, it's important. All right, you need zero. The character set, as you're aware of already, all right, for Babylonian, it's really just two things. Wedge like that, wedges like this in tandem, all right? So I personally, not to corrupt your opinion, I like to call it a wedge and a boomerang, or a railroad spike and a boomerang, or a nail and a boomerang, all right? And it's just representative of 1 and 10. Even though it's a base 60 system, that's what they had to work with. Right? That just means that the multiplier is 60. Don't go to sleep, mommy. I'm not that boring. Okay. The character set that you're working with insofar as Mayan is concerned, basically it's 0, a dot in sequence, or a line. So you have zeros, you have 1 to work with, and you have 5. Let's see. And our character set, being its base 10, starts at 0 and runs up into 9. Right? There are 10 characters total. All right. Remember, a positional value system, right, ideally would be 0 and all numbers less than the base. Right? It's technically, in the case of the Babylonian system, it's defying that characteristic, right? Because they don't have a 0. They simply wouldn't draw it, right? But and this is not technically base 20, all right? Neither of these is a purity of this definition of a base system, right? A positional value system. It does include 0, but it also doesn't just include 20. It includes 18 at a certain point, right? Our decimal system cuts the mustard, right? It meets both requirements, all right? We have a base number, 10, and then we have a character set that starts at 0, and it has 10 total, right? It's all up to the number less than the base. So in our case, less than 10. Okay. I mentioned before, and it's still important. I need a little bit of space, so I'm going to move this up just a wee bit. When you see a number or something, and then the wedge and the boomerang pointed this way, let's just call it a flukerang and a wedge, and then there's a number on the opposite side. This means subtract. Okay. What else can we do? As I mentioned earlier, I'll just put this here. 18 is incorporated, right, to conform to 360. Okay. Now, how did they get the point across of positions in the case of the Babylonian system? All right, they make gaps to illustrate position. I hope that that's visible. That's not gas. Sorry. There are gaps to illustrate position. All right. In the case of the Mayan system, it's a little bit more comfortable because you don't have to worry about somebody having sloppy handwriting. Instead, what they do is that they stack to illustrate position. And that's more like traditional Chinese. Right? So when you're dealing with Babylonian, look for gaps. When you're dealing with Mayan, make sure that you're using a stacked sort of array. All right? All right. Now, last thing I want to show you is how it actually would pan out if you had to calculate. I have to sneeze, I'm sorry. Anyhow, let me erase this now. These are the models that you would basically employ when you're translating between the alien system and the familiar system. Right? So have this on hand, at least if it is elucidating, right, when translating. Right, specifically to or from Babylonian or to or from Mayan. All right, you're going to see groups of symbols. All right, and you're going to build up somewhat counterintuitively from the right to the left. That's why there are ellipse marks here, because you could keep tacking on more terms here. All right. Usually you don't need this many, but just to get the point across, start with this sort of a scaffold when you're trying to figure out what the Babylonian symbols relate to. All right. The group that you see, all right, there's a gap group, all right, and then there's a second one, a first group, a second group maybe, perhaps a third. You would have to, because of its position value, multiply by 60 to the 0. What does that realistically mean? It means multiply by 1. Right? Because 60 to the 0 is 1. Right? You could validate that with a calculator. Otherwise, you'd have to go into the quotient rule. You know, 60 to the first is essentially you're going to multiply by 60. Right? The third group would be 60 to the second, which would be 3,600. Right? And further and further. 60 times 60 times 60 times 6. 0, 0, 36, carry the 3, 18, and a 0. 200, this one when you get to the third one is terrible. Right? 216,000 is in theory what you would be multiplying by. Something like that. Let's see. 6, 18, and 3 again, 21. Okay. So, just realize that that is the style of writing the number 3,600 in a base 60 system. This is the style of a number in a base 60 system. This is the style of the number in a base 60 system. All right. Whatever you calculate the group to be, you would have to multiply by that. Whatever you calculate this group to have to be, you multiply by 60. Whatever this group is, you multiply by 1 technically. All right, and the same thing over here. All right, you're probably never going to have to go this far. Right? If you think back to Egyptian, right, you know, 1,000,000 was an astounding sort of figure to them. All right, so the Babylonians being their contemporaries, they were probably equally impressed and awed by very large quantities. The Mayan system is stacked. All right, and since it's base 20, as you see, that's going to be times 20 to certain power of 20, power of 20, power of 20, power of 20, power of 20. But here's how it works here. All right, it's the group that you see written in Mayan on the very bottom level times 20 to the first, which again really just means you're going to multiply by 1. This is times 1, right? The group that you see on the second level, level 1, we're calling it versus level 0, the royal we, right, is times 20. This is the first power of 20. When you get to the what is really technically the third level, let's just call it level 2, keeping with 0, 1, 2, as in the exponents here. Technically, it would be the first 2. It starts at 20 to the first again, right? But that incorporates 18, right, as I mentioned. If this is really just 20 and that's really just 18, the number here that you're multiplying by is 360 because it's 18 times 20. All right. And then the next one would be 400 times 18, which I want to say is 7,200. 7,200 is really the multiplier. And then if you get that far up that you have 1, 2, 3, 4, 5 levels technically, this group, whatever you determine it to be, would have to be multiplied by, is it 800 times 18? Or 8,000? 20 times 20 is 400. 400 times another 20 is 8,000. So 18 times 8. 64, carry the 6. 140, yeah. 144,000. Something like that. Let me validate here my calculator. Let's see. Yep. Okay. That's crazy. It's correct, but it's crazy. Okay. All right. So the hard part will just be translating the groups that you see stacked, right? And then you could use your calculator to multiply by those values. Okay. So let's get into some examples now, as I've dawdled enough. All right, and with that in mind, let me maybe turn off the projector now, because I don't think I need it. Okay. And pull back the button. All right. Let me turn the light on. There we go. Let's see. In the packet that I have, as I mentioned, you can follow along if you want to print out the problems. They're in green, sort of. These are swiped from the textbook. I left the solutions in just in case, this is, it's a little weird. All right. So, anyhow, let's just do these. All right, and I'll try to conform myself to just working in half a board at a time here. Okay. We're doing more translation. Okay. Example 1. Example 2. I don't like it there. I think that was without symmetry. Okay. All right. Let's say that you start with Babylonian. So just to get the instruction across, it's baby, maybe baby, and we'll convert it to our system, Hindu Arabic. So H-A. All right. If you're starting with this and you're converting to this, all right, here's what you might see as the character set. Pardon me, the symbols as they're written. Imagine you had in sequence a boomerang, 3 boomerangs, and 4 wedges in clay. Then an obvious gap, and then 2 boomerangs and 1 wedge. Impressions in clay. All right, remember that it's a little counterintuitive because we're used to reading from left to right, and this system would start from the right. Okay. So this is a group. And since we're going to start from basically 60 to the 0, it would be times 60 to the 0. Whatever we interpret this to be. Remember, there's not a lot of their characters. All right. Then the second grouping would be here. And we would have to up the ante by 1 here. 60 to the first. All right. And eventually, add these. So, if the character set for Babylonian is just these 2 symbols, a wedge and a boomerang, and they represent essentially 1, and 10, right? Let's just count these, right? They're similar to Egyptian in that you basically could, if there's more and more iterations of them, the repeated character, you would just add them. So if this is really 10, 10, 10, 1, 1, 1, 1, what is that in total if you added them? 10 and 10 and 10 is 30. 30 plus another 1, 1, 1, 1 is 34. So this first group is really 34 times 60. Right. The next one, it's really 10 and 10 and then 1. So that would be this first group technically is 21 times 60. 60 to the first is really 34 times 60, which makes this 2040 just by itself. 21 times 60 to the 0 is really 21 times 1, right, which makes this just 21. If you added these, you'd get 2061 as your outcome. Okay, so just a bunch of clay wedges and boomerangs, while impressions in clay means that number. Okay, it's interesting, isn't it? Here's another one with a little extra group. Example 2. We'll do the same thing here. We'll go from Babylonian to Hindu Arabic. So if you had a boomerang, a boomerang, a boomerang, and then, no, too many, sorry. I'm looking at the wrong thing, I'm sorry. Pay attention to one. All right. Sorry, 2 wedges to start with. Fangs, there you go. A gap, a boomerang, and then a wedge. And then this sequence, a boomerang, and then a flukerang, wedge, and then 2 wedges. We can translate. Right. The downside to this is that there can be some confusion if the gaps are not obvious. Right? So if I were going to do this as a scribe in ancient Sumeria or elsewhere, all right, I would try to make this as obvious as possible. Right? I've already kind of fudged it, as you can see, but we're going to again start from the very far right over here. And we're going to say to ourselves, okay, this is going to be a group that is times 60 to the 0. And then this is going to be a second group times 60 to the first. And then this is going to be a third group in this case. That's going to be 60 squared. And then, having set it up that way, we'll have to remind ourselves eventually we're going to add 2, right, these places. All right, now, you could start here, certainly, but that's the most complicated thing, was the flukerang here and the wedge. So what I'm going to do is I'm going to start with the easy ones, because you kind of have some familiarity with that first. And then when we get here, it's not going to be too bad, but I'll do the more traditional thing. Set it up from right to left, and then you could work in any order that you want, as long as you see what the plan is. This is, again, our character set of a wedge or a boomerang. So it's either 1 or it's 10. And these are 2 wedges in sequence, so that's 1 and 1. That makes this first group really 2 times 60 squared. All right, that means it's really 2 times 3600. All right, which is really 7200. Okay. This is a boomerang and then a wedge, so 10 and then 1, which makes this second group 11. And therefore it is really 11 times 60, which would be 660. And then this one is more complicated because of the so-called, I'm just dubbing it this, flukerang wedge combo here, which means subtract. Right? You have the equivalent of 10 and 10, which makes this 20 minus something. And then you have the combination of 1 and 1, which is really just 2. So it's really saying from 20 subtract 2. Right, which makes this what really? It's 18. What is that really? Since it's 60 to the first, that means that's really 18 times 1, which means that this is 18. Right. And now we will add all of these to each other. And I'll just stack them here because it makes it easier. 660 in on graph paper. These would be nicely collimated here. So again, give your students graph paper when you're teaching them how to add and subtract, especially, right? Because they need to, even if they have sloppy handwriting, the scaffolding will help them and they'll be less likely to make a mistake. We're just adding, so I'll do 3 things in sequence: 8, 7, 8, and 7. So what you should get for this is 7,878 is wedge, wedge, boomerang, wedge, boomerang, boomerang, flukerang, wedge, wedge, wedge. 7878. 7,878. It's funny, isn't it? All right. Now, to kind of give you an idea, all right, you could, just being aware of what the scaffolding looks like and what the symbols translate to, you're probably not going to have any issue, all right? If you have to convert from an ordinary number, though, which is what we haven't done yet, all right? I did try to come up with a set of instructions, and I'll show you that now. Let me erase this to free the space. Blue writes so nice, but it never goes away. I don't know why it's like that. Everything else is really easy to erase. Wake up. There you go. Ow. Okay. There's this idea that I came up with to try to give you procedures, right? I'm dubbing, perhaps, I don't mean to be unkind about it, the systems that we are not generally familiar with as alien. Right? So, what is alien? Babylonian is alien, right? Not too many people write in Babylonian anymore, outside of archaeology, perhaps. And I'm dubbing what is familiar the Hindu-Arabic system, because that's what we do. Basically everybody on Earth uses it at this point. Okay? So, to generalize, anything that is not familiar is alien. What is familiar is exclusively this, Hindu-Arabic. All right? This set of symbols that we all know and love. Base 10. All right? So here's the idea. If you're converting from something alien to Hindu-Arabic, or when we get into section 4.3, it doesn't have to be Babylonian or Mayan. It could be anything that's a weird base to base 10. All right? If we're basically going in this procedure, all right, as we had done a few moments ago, what are you doing but multiplying, really? All right, that is it in a nutshell. And I put some more procedures to kind of guide you, but You might have an intuition about it right now, and I don't want to screw that up. Just make this distinction. Alien to familiar, multiply. Okay? If, on the other hand, right, you're going the other way, you're starting with the familiar system, Hindu-Arabic, right, and you're converting to the alien hieroglyphics. Because you were going the other direction, you're going to end up dividing, basically. That is, there's more to it than that, but convince yourself. If this is the train of thought, familiar to alien, divide. Alien to familiar, multiply. Familiar to alien, divide. They're opposite operations, right? This is a bit of a summary here. We're going to start with the usual ordinary number, and we're going to convert it to the alien hieroglyphics. When, again, we get to section 4.3, we're going to be talking about Hindu-Arabic, but we're going to be referring to its base. Right? We're just not going to use this phrase anymore. We'll call it base 10, because that's what it is. Right? And then we'll convert it to base X, whatever that is, whatever is unusual. Right? There is a sort of nomenclature for this in symbols. What do you call it? Notation. A subscript is implying what the base number is, right? So if it's n, slightly smaller font, a little bit lower subscript, base 10 is how you would write it then. You don't really have to worry about this. This is section 4.3, all right? What we're doing right now is section 4.2. Okay, and to do this, it's a little bit more complicated, so here's the list of procedures to get you through it. You could use your calculator, certainly, but it's kind of there just to resolve any arithmetic error. Right? Step 1 is, step 0. Identify the position values of the alien system. Right? So, for example, if you know that you are working in Babylonian, then you know that the position values would be 60, 0, 61, 60 to the second, and technically 60 to the third, and it would go on into infinity. What is the value of these powers of 60? 60 to the first is really the number 1. 60 to the 0 is really 1. 60 to the first is really 60. 60 squared is really 3600. And 60 to the third is 216,000. Now, hopefully, you won't need to go up that far. But in theory, it is possible. And for the sake of comparison, you may need to establish that. 216,000. These will be your divisors, right? I.e., what you divide by. I.e., as in other words, right? What you divide by. Right? Step 1 would be compare these values, right, to what is given to you in Hindu-Arabic. So when this situation arises, that the thing that you are given, if the given value is less than the position value, one of these things, one of these, right? Don't use it to divide, use the next lowest place value to divide. Right? You're really looking for the point at which this shifts to being greater relationship. Or equal, you can get away with using equal as well. Right? But if it's like this, if your given value is somehow smaller than these numbers that you're comparing it to, you can't use it divide. It wouldn't technically fit. All right. Next thing. When you're finally dividing, circle the quotients. All right, remember that when you're dividing, there are these parts, at least if you write it in the orientation that is familiar to the United States. All right, the number that is inside the box is the dividend. The number that is on the outside, i.e. what you divide by, is the divisor. And the answer up here is the quotient. All right, so what you want to do is you want to circle the quotients, and because you're going to be dividing usually in several steps, right? And you want to use this as part of your answer. All right? You're going to end up with a lot of remainders, though. Continue dividing the remainders to the last position. In other words, if you use the number 3600 in your first division, good, but you'll probably get a remainder. And then what you're going to do is divide by 60, and then you're going to get a remainder, and then you're going to divide by 1, you know, and that whatever that quotient is, which is usually the same number. All right, you're going to circle the 3 quotients that you get. All right. Now here's what happens. Each quotient will represent a group. That's why you're circling them, because you need to include them, incorporate them into your answer. It would look like this in theory. The group times whatever the power, right? Plus the group times whatever the power, plus the group times whatever the power, and so forth. All right. Then you have to finally translate the groups. You don't have to actually multiply, but you have to translate the groups into the Babylonian system that you're limited to, which means that whatever number you have in Hindu-Arabic, and the division would be in Hindu-Arabic, you're going to have to translate into boomerangs and wedges, or into dots and lines and footballs, right? Or whatever the alien character set is. Okay? It's involved, right? And I wouldn't expect anybody to go, oh yeah, it makes perfect sense the first time, but this is basically the train of thought, right? If it helps, again, just say to yourself, when I'm converting from what I know to something that I don't know, the alien system, you're dividing. When you're going the other way, you're multiplying. All right? Let's do a few. Put this light back on, and I'll turn my projector off because I don't think I need it anymore. Alright, and we'll do this. Natural light is good. Okay, so again, I want to try to confine myself to a certain portion of the board here, so I don't have to erase that much. Translating still, but we're doing it the other way. Alright, this is technically going to be example 3, and I'll do example 4 over here. Alright, and the basic instruction is this. Alright, we will be converting from, I wonder if this is a little bit more faint, I can get away with using this. Hindu-Arabic to Babylonian. All right, that's the train of thought. All right, so again, what is familiar, my fam, all right, to what is alien. Alien. All right, not a bad thing if it's an alien, but it's not. You're not used to it. Right, is the point. And since this is the train of thought, I know that you're probably going to divide, okay, at some point. Now, let's identify the position values. All right, if we're talking about Babylonian, we know that we have 60 to the 0, 60 to the first, 60 to the second, maybe 60 to the third, hopefully not that. And that what they correlate to is really the number 1, the number 60, the number 3600, and the god-awful 216,000. Okay? These are the things that in theory we would be dividing by. Okay. All right, so what is the number that we have to work with? Let's say that we're translating this number, 2,519. And we're going to translate this standard, familiar, Hindu-Arabic number 2,519 into Babylonian. All right, I am now going to compare this number to these position values that are established. So, all right, the number $200. Let me put this in black just to make it a little bit more distinct here. Sorry about my shadow here. 200, pardon me, I don't know why I want to keep saying 200. 2,519 is what compared to this. It's less than 216,000, so we can't use that. All right. 2,519 is less than 3,600, so we really can't use that. But what we're going to get to is that 2,519 is greater than 60. All right? What we're always looking for is this point of transition, either this or if it were equals. All right? If this is the relationship, that it was 60 equals 60, all right, then that's what you're going to divide by. All right? But if we have something that is greater, the given thing is greater than the position value, that's the thing that we're going to use to divide into this number, 2,519. Okay? Use this. 60, and you could use your calculator, but just realize that the unfortunate thing about a calculator is that it doesn't do remainders really. It gives you the decimal equivalent, or in some cases you can get a fraction. But and then in the case of a fraction, maybe, then you could go, all right, well, the top of it is the remainder, at least if it hasn't been simplified. But we'll see. 60 goes into 2, too small. Goes into 25, too small. But it goes into 251, take a guess, all right? Look at it as the relationship between maybe 24 and 60, 24 and 6. That would be about 4, right? So above the 1, I would put a 4. And then I would have the number 240 here. That's probably as close as you're going to get without overshooting the number itself, 251, all right? 4 times 60 is this, which we're going to subtract. Basically doing long division, all right? Now, if you subtract 1 and 0, you get 1. If you subtract 5 and 4, you get 1. And if you get 2 and 2, it's 0, which if you want, you can put a 0 here or ignore it. Then you bring down the next number, 19, and you do it again, all right? And again, you say to yourself, you make an educated guess. How many 60s can you squeeze into 119? If it was, this was 12, and that was 6, and that is just 6, then it would be exactly 2, all right? But this is a little shy of that. So it would have to be 1, unfortunately, right? In which case, you're gonna have to subtract the 60 itself. 1 times 60 is 60. So there's what you're subtracting. I'm probably going to need the space, so let me just erase that. All right, now you go through the motions here. 9 minus 0, 9. 11 minus 60 is just 5. So you have 59. We're not doing decimal long division, and we're not really doing fractions. What we have here is a remainder, and we kind of want that. It's a rather large remainder, 59, but we need that number. And unfortunately, a regular calculator can't give you that, so at least not with consistency. So what we now do is we're going to take the number 59, the remainder of 59, and we're going to go through the next position value. We just used this one successfully. All right, but we got to exhaust all possible position values. So the next one is in fact 60 itself. So what's the number that we're going to divide by? The number that we're going to divide by is 1. So that's not too hard at all. All right. I did forget to circle this because I do need it. All right. So what's 1 into 59? It's exactly 59, right? 1 goes into 5 times exactly, terminates. Then you do the next digit, 1 goes into 9 exactly, 9 times, and it terminates. So these are the two groups that you have. This is the first group, value. This is a second group value. Okay. So if the model that we have to work with, as discussed from earlier, looks like this, is 60 to the 0 times a group plus 60 to the first times a group. We don't actually have to multiply because we're going from ordinary number to the alien system. But we would have fitted the values of the groups in here and in here. So I'll just squeeze in 41 in here just for reference, and 59 in here just for reference, right? It's really came from what? It came from multiplying by, dividing by 1. This is really a 1 here, and this is really a 60 here. Okay, it is these things that you see that represent the group in Hindu Arabic numerals that we now need to translate using the Babylonian character set, which is this and this. So this has to be interpreted in terms of these symbols, and this as well, with an obvious gap in between them. So because I'm running a little shy of space here, let me sort of confine myself to just this portion of the board here. All right. You have the quantity that represents 1, and you have a quantity boomerang that represents 10. And how do you illustrate a number? It's very similar to ancient Egyptian hieroglyphics in that you just repeat the symbol. All right. As a matter of fact, the one downside to the Babylonian system is that it can get very inefficient if you're not careful. And it's technically allowed. There may be more than one way to write something is what I'm getting at. But maybe let's just do it intuitive first. We'll do simple adding. How would you, you could put in theory 41 wedges, right? But that's not too efficient, right? So if you're a good scribe, you go like, I'm wasting clay. All right, so don't waste the clay. You know, people nowadays go, oh, you made me print stuff. Oh, the paper, the forest, and you should care about trees, but no, don't make excuses. So anyhow, the more efficient thing than writing 41 ones essentially would be to use 4 boomerangs for 10. So here's my 41 here. Boomerang, 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 wedge. And I'll make them a little bit more obvious. You don't understand, you're wasting clay. Alright, and it might look something like that for this group here. Alright, that's 10 plus 10 plus 10 plus 10 plus 1. Alright, or, alright, then you have, and then you leave a gap here. There's a gap, not in the mold, alright? And then you express 59. Now, you can do, in theory, the same thing. You could do 59 individual wedges, alright? But then you'd be a lousy scribe, right? And you get fired for wasting clay. So, rather than do that, what you can do is, I'll show you 2 ways to do it. You could do the similar thing, which is to make 5 boomerangs, right, to represent 50. And then, because I'm running out of board space, you could do, in theory, 9 wedges, but even that is not the most efficient thing to do. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is one possibility. Right? What would be more efficient, though? More efficient than adding, in this case. More efficient in the sense that you're using less clay, you're using less wedges. All right? 10, 20, 30, 40, 50, 1, 2, 3, 4, 5, 6, 7, 8, 9. Subtracting. All right? So, because I'm really running out of space, here would be the best course of action, I think. Rather than write 9 wedges, right, you can do a subtraction, which is just adding, right? You could do a subtraction problem. So here we have over here, 41 is represented by boomerang, 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 wedge. Gap. 59 would be boomerang, 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 boomerang. And then this problem. An extra boomerang, which I'll just make in red because it might make it more distinct. So that's 5, 10, 15, 20, pardon me, 10, 20, 30, 40, 50. An extra one would be 60, right? Then we could employ the symbol for subtraction, that combination, which again, I'm just dubbing it this, it doesn't really have its name. Flukerang, wedge. And then how would you get to 60 and subtracting instead? How would you get to 59 by subtracting instead? It's 60 minus what? 1. I'll put it in red. This is more efficient via subtraction. In this particular case, okay, so if a person writes that, it's correct. A person, again, could do 41 wedges and 59 wedges in theory, right? But it's taking up a lot of space, right? So as an efficient scribe, you try to be as, concise as possible to convey the same meaning. All right, that's kind of cool, isn't it? I think so. All right. Anyhow, I would do that. All right. And do leave an obvious gap because you don't want to make it seem like it's something else. Let's see. Let me skip over 4 because it's really the same thing again. But I'll look at 5 because it's a little bit tricky. And then we'll do 6, which is Mayan. Because we're at an hour and a half now. Okay. These types of problems, maybe I should even bother partitioning because they take up a lot of space. What time is it? Almost 3. Okay. So here we go. All right, we're still translating. Let's do this one. That is example 5. We're going to convert Hindu Arabic to Babylonian. This problem will be basically illustrate it was not a perfect system, and you'll see why as we go through this. All right, if the original number is 7,223, and we established that we have these figures to work with: 60 to the 0, 60 to the 1st, 60 to the 2nd, 60 to the 3rd. And their equivalents are, let's see, 160, 3,600, 216,000. What will we start dividing by as we compare here? All right. Well, 7,223 is significantly less than 216,000. So we're not going to use that one. 7,223 is greater than 3,600. So we're going to start here when we divide. We'll use this to divide. 3,600 into 7,223. If the relationship were just 36 and 72, then it would be exactly 2, right? So 3,600 times 2 would be 7,200. You could use your calculator to verify what the whole number is at least, but you do need to go through the minutiae to get to the actual remainders, the intricate work. So 3 minus 0 is 3, 2 minus 0 is 2, 2 and 2 is 0, and that would be 0 technically as well, so we don't really have to include these. That's the remainder. So we're going to use this remainder. Are we on time? Still ticking away, good. Here. So we have, since we've used this one, we're now going to use the next number. The remainder goes in the box. Right? This remainder goes inside, remember. And the next thing that we have to divide with is 60. Now what's going to happen though? All right. Does 60 fit into 23? All right. No, it wouldn't work, right? And if we were doing decimal division, we would put a decimal point here and then look at it as 230 instead. But what we're going to do, because we're dealing with remainders and not decimal division, we're going to say, no, it's not going to work. It's just 0. All right? It's too big. All right? And then what we're going to do instead is, having established that this doesn't work in the middle here, is go to the next one, which is use 1 instead. All right? We used 3,600 successfully. We've tried to use 60 because it was in the way, you know, it doesn't work though. And then we're going to now go to the end because we have to always go to the end. So the number is still 23. All right, but let's see what we get. All right, does 1 go into 23? It does. All right. So 1 goes into 2 exactly 1 time. It terminates. 1 goes into 3 exactly, pardon me, 2 times. Sorry. And then 1 goes into 3 exactly 3 times. All right. I should put this in the consistent color of blue just to make sure that we know that that's what we're going to use. Okay. All right. So for right now, just circle these because these are our groups in theory. All right. This would be first group. All right. This in theory would be a second group. And this would be a third group. All right. If I were going to use this as part of the model that is the Babylonian model, just give myself a little bit of space here, we would have this, right? We would have, well, if we have 3 groups, it would be 60 to the 0 times that group, plus 60 to the first times that group, plus 60 to the second rather, times the next group. And I've kind of tucked myself into a corner here, so I'm going to squeak this in group. All right, sorry for that. First group, second group, third group. That quantity, that one technically, and this one. All right. Which if I just kind of put them in here, all right, the first one is 23. This one is technically 0. All right, again, why is it 0? Because if we were doing decimal division, we'd have to say, no, it doesn't fit in here. All right, it's too small. All right, but then we would expand it to get the decimal number here. We're not doing decimal division, but that would be the quotient, 0 point something. All right, they don't even know decimals, the Babylonians, so don't really stress about it. Just use 0 to fill in the void. Group. All right, and then we have this number 2. All right. Now here's where we get into some trouble. All right, translating 2 is not so hard. Translating 23 is not so hard either. But the way that the Babylonians used to write this is that they may not have put the gap here that they should have. You know, it can get confusing. It would be correct, but it might be ambiguous is the problem. So let's straighten out what we can. All right. The number 2, using Babylonian symbols, is just a wedge and a wedge, right? And it comes from this times 60 squared, which is times 3600, really. But then there's this thing here, all right? They didn't have the symbol for 0, all right? So we can't put a symbol here, all right, to represent this, all right? There's nothing for that, unfortunately. Then there's this, the 23 portion of it, all right? That's not too bad, right? It would be boomerang, boomerang for 20, and then 3 wedges to represent this times 1 versus this times 60. If the scribe who was writing this, all right, put these things a little bit closer though, the ambiguity would be that, oh, well then it's 2 times 60 instead of what it really should be, which is 2 times 3600. You see what the problem is, all right? The point of this is meant to illustrate this was not a perfect system. All right? The only thing that you could really do to compensate is to make an extra wide gap. All right? To make sure that in theory a person is not multiplying by 60 when in fact they should be multiplying by 3600. All right? This is correct down here, but it's ambiguous. This in tandem with this is correct, but ambiguous. And that's not good. Math should not be ambiguous. Don't fool yourself. All right, now we're going to do the Mayan system, and then we're almost finished. It's really got a buff sometimes. Again, I like writing in blue, but it doesn't go away. All right. Now what we're going to do is we're going to start by converting from Mayan into Hindu Arabic. All right. So again, what is technically alien to most people to what is familiar to virtually everyone. And therefore, if we're following this train of thought, alien to familiar, trust that you're going to multiply. You're just going to have to multiply conforming to the system that is the Mayan-based 20 system with occasional 18s thrown in there. All right. Now let's say that you had these symbols. All right. 2 dots, 3 dots, and a line. Sort of a sideways circle here, and then 4 dots. All right. What you should start always from the bottom. That's probably the easiest thing to do. And I just to give you some kind of scaffolding, I'm going to very faintly draw in green sort of levels here. Think of it like an elevator. All right. This bottom here, since 0 would certainly not be incorporated with dots here, all right, is the bottom level here. All right. And then this 0 is the next level. All right. And then these in tandem would be a 3rd level. And then this is the 4th level. All right. The Mayan system, again, is totally cool because it's very intuitive, right? Let's start with this. All right. You can do the translation almost immediately without even having too much of a key or anything. This is 1, 2, 3, 4 dots. That represents the number 4. This is a sideways sort of circle, sort of a coin on its edge, if you will, or I don't know, it kind of looks like a football to me too. That is the number 0. All right. These are 3 dots and then a line. Remember, a line is 5. So if it's 5 and then 3 dots, that would make this 8 intuitively. And then these are just 2 dots, which makes this 2. All right. That's not the answer though, because remember you have to multiply by the positional values, and it's a base 20 system. So what is really going on here now is it's this number times the respective position value. Right? If the position values are stacked from the bottom as the group, whatever it is, this is a group, right? Times 20 to the 0, that really just means 4 times 1, right? I'll come back and straighten that out in a minute. Right. But just beware, it's going to increase the power of 20 by increments of 1. So this would be times 20 to the first. And then when you get to the next level here, after 20 to the first has already been accounted for, you're going to do 20 to the first again, but you also have to multiply by 18. All right? The third level is always bringing in 18 into the fold, into the mix. So now this is 20 squared times 18. What does that really mean? It means that you're multiplying 4 times 1, right? Because 20 to the 0 is 1. 0 times 20 to the first is really times 20. 20 times 18 is really times 360, right? And then 20 squared is 400, and 400 times 18 is 7,200. So you can multiply by 7,200. Let's see. Blah, blah, blah. Yeah. What you get up here two times 7,200 is 14,400. 8 times 3,600 is what? Oh, 360 rather, sorry. 2,280, pardon me, 2,880. 0 times 20 is just 0. And 4 times 1 is just 4. And again, if a good, as a good teacher, I give your kids graph paper if they're doing this by hand, you know, so they could very anal retentively collimate. When you add, it helps, all right? I don't mean to be a stickler, I'm a Ziegler, all right? But that's how you could circumvent the issue. You got to get kids to write. It's very important, physically write things, all right, verbally and numerically, all right? And make sure that they, when they're adding or subtracting, they got to collimate. All right, it's very important. So what do you get? If you add 0, 0, 0, and 4, you get 4. All right, if you get 0 and 8, you get 8. If you get 4 and 8, it's 2. Carry the 1, and it's 7, and then carry down the 1. 17,284 is illustrated in Mayan here. 17,284. That is technically example 7, but so what?
You're going to have to call a new number. Would you like me to provide that for you?
Alright, so it's a little redundant. That's fine. Alright, let's do one example that you go in the other way from Hindu Arabic to Mayan.
Okay.
And then we'll be done for today. Now the green is sticking. The green is causing me trouble. Maybe it's my eraser. Maybe I have to invest in a new one. Here's our last example. This is technically example 8. The other one was 7. All right. If you were converting from Hindu Arabic to Mayan, all right, we're starting with what is familiar, and we're going to what is alien. All right. So if that's the case, we eventually are going to have to divide. Okay. If the number is 4025, all right, let's establish what the position values are in Mayan. All right. We know that it's in stacks normally, all right, and the bottom level is 20 to the 0, which means that it's 1. That's the position value. And then 20 to the first, which is 20. And then 20 to the first times 18, which is 360 intentionally. And then 20 squared times 18, which is 7,200. If we went another one, which you probably don't have to, it would be 144,000, I want to say. Anyhow, let's see if we can get away with just using these for sake of comparison. These are the position values. Okay. The number 4025 is less than 7,200. So we're not going to use that one. The next thing is 4025 is in fact greater than 360. So this is where we're going to start here. All right, we're going to use this to divide. 360 into the original figure of 4025. Again, you could use a calculator if you want to establish what the first, or maybe up to what technically would be the whole number. That's fine, but you have to go through the intricate work of it every time to get the actual remainders. So you could muddle through, right? 360 fits into 400 roughly one time, which is 360, all right? Do the subtraction. Again, graph paper would be ideal if you're doing this by hand, just to keep it neat and orderly. 2 minus 0 is just 2. This becomes a 10. That becomes a 3. This is a 4. So you have 42, and then you drag down a 5 here and redress the 360. So how many 360s can you squeeze into 425? Probably no more than one again, right? Which is 360, and you subtract. So you have 5, that becomes 12. 12 minus 6 is 6. Right? This is, again, your remainder, which is what you want. But you're going to use it in the next position value here, no matter what. If it doesn't fit, you put a 0. So if the figure is now 65, and the position value is 20 for the next one, since we've done that one, we continue. All right. How many 20s can you fit into 65 roughly? 3, which is 60, and the difference is 5. And we're not doing decimal division, so we're going to continue. This next one. And now we have black here. You have a 5 as the dividend, and we have used the 20 here, so we're going to go to the next one, which is dividing by 1. That's super easy. All right. How many 1s can you fit into 5? Exactly 5. All right. It is these quotients that we have here that we're going to translate into the system. All right. So I need a little bit of space. So what I'm going to do is I'm going to create a stack. All right. And since this is the bottom rung here, start from the bottom, we have our 5, the equivalent of 3 here, and then 11. So we're going to start from here and go up. All right. What is the symbol for 5 in the Mayan character set? It's just a line. All right. So you would have this at the very bottom. What are the symbol for 3? Up to 4 and up through including 4 you use dots. So this is just going to be 3 dots in sequence. And then for 11, it's 10 with an extra 1. So that makes it 2 5s and then a 1 on top. All right, not too bad, right? And this, without the lines, is the Mayan equivalent of 4025. Dot, 2 lines, 3 dots, 1 line. Okay. I believe that is it for today. It's quite a lot to digest anyhow. Let me leave it at that. Okay. Naturally, for homework, if we're sticking with the schedule, and we should, just not to let it get away from you. Just remember, for homework, do section 4.2 in MyLab. Right. Ideally, you would have done 4.1 in the prerequisite yesterday. Okay, but this would be good to keep pace. All right. Thank you guys for listening. I'll see you again tomorrow. Be careful out there.